Fractals and nature. We will continue talking about it next class as our last sort of little mini topic of the semester. So there's lots of group work today, so we're going to go through the lecture part quickly. A fractal is a geometric object defined by a recursive process. So that's where you apply the same procedure over and over and over again in an infinite feedback loop. So the output at one step becomes the input at the next step. So we're going to start our study of fractals with an example. It's called the Koch Snowflake. And as we study this and other examples, we're going to develop some knowledge and vocabulary surrounding fractals in general. So here's how you build the Koch Snowflake. You start with a shaded equilateral triangle. We call this the seed of the snowflake. So then to the middle third of each side of the seed, you add an equilateral triangle. So I'm just going to take on the middle third of each side, I glue on a smaller equilateral triangle. So this is what I get at step one, this picture right here. And then you do it again. So to the middle third of each of the 12 sides. So at step one, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides, right? On the middle third of each of those, we add another little equilateral triangle. And that gives you step two of the Koch snowflake. And then you just continue doing that over and over and over again. To every side of the snowflake, on the middle third, you add a new equilateral triangle. So these are the first several iterations. At every step, you add equilateral triangles to the snowflake. But at some point, those triangles are so tiny that it's hard to even see the changes that you've made. So eventually, there's actually no difference to the human eye between one snowflake and the next. So any drawing of the Koch snowflake that we make, regardless of how many iterations we perform, is just an approximation of the actual Koch snowflake. The Koch snowflake is the shape that we would obtain if we could actually carry out an infinite number of iterations. So therefore, it's an abstract object. You can never actually create the Koch snowflake because it's something that only exists, in infinity, if you could do this for infinity. So it's an abstract object. So we can only conceive of it in our minds. We can't ever actually build it, but there are still some concrete facts that we can know about the Koch snowflake related to its perimeter and its area. So suppose the perimeter of the seed is 27 units. What would you guess is the perimeter of the infinite Koch snowflake? So let's go back and look at the picture. So this guy has perimeter 27. If I keep adding more and more and more triangles on, what's happening to the length of the perimeter? It's getting longer. Does it ever stop getting longer? No. Okay, so our guess is that it would be infinite, right? Okay, so if my perimeter of the infinite Koch snowflake would be infinity. So let's say the area of the seed is 35 square units. What would you guess is the area of the infinite Koch snowflake? Infinite? Okay. So we keep adding more triangles on. We're adding area, so it seems like the area is just going to get bigger and bigger and bigger, right? All right, so we're guessing, because this is an infinite object, we'll have infinite perimeter and infinite area. Okay, so we're going to come back to these guesses later, and we'll try to reason out if they're right. But first, we're going to talk about the self-similarity of the Koch snowflake, or any fractal in general, actually, has self-similarity. That is that the object is similar to part of itself, which is in turn similar to an even smaller part, and so on. So in other words, if you zoom in on a small piece of the edge of the snowflake, it looks exactly like the snowflake itself. And you can keep doing this forever. You can keep just zooming in and zooming in and zooming in, because this is an infinite object. So I have a short clip. If you get motion sick, you might not want to watch it. So if you go to YouTube and Google fractal zoom, you'll find tons of things like that with different fractals, and it's like crazy. Yeah. So many fractals exhibit this property of self-similarity, and in the case of the Koch snowflake, the self-similarity is infinite, meaning you can zoom in forever because it's an infinite object. You could just, we have to stop the video at some point, but you could keep going and going and going, keep zooming in, and it will keep looking like itself. So that means it's infinite. Universal, which means you can zoom in anywhere. You could tell in that video we were kind of zooming in different places, and it just kept looking like the snowflake. And exact, looks exactly the same when you zoom in. Lots of fractals and self-similarity exist in nature, but in practice, self-similarity can't be infinite because anything in the world is finite. And it can't be exact because there are always slight variations when you look at anything in real life. So these are examples of fractal-like things that we find in nature where you can zoom in and we have self-similarity. So here I have this fern, and each little leaf on the fern is like a miniature version of the fern itself. So we have self-similarity, but it's approximate because it's not exactly like the big fern. And then each little tiny leaf on each leaf of the fern is also a little miniature version of the big fern, but that's as far as we can go. You can only zoom in 3 times. Right? So we have lots of these examples here. This is a kind of cauliflower broccoli hybrid, and it's edible. And you also might notice that it's got spirals. Fibonacci, yep. If we counted the spirals, there would probably be Fibonacci numbers. In fact, let's do it. That might be fun. All right, let's see. I don't know if the picture's clear enough for me to be able to count them. Yeah, it's not. This is called a Fiddlehead Fern. And so you can see, it's got one major spiral. And then it's got little tiny spirals that are miniature versions of the whole fern. And then on each little spiral is a little teeny tiny spiral that is a miniature version of the whole fern. This is a picture of a coastline. It's got self-similarity, definitely not exact, but if I were to zoom in on one area of that picture, it would be hard to tell the difference between the 2 pictures. They would look pretty similar. And lightning or anything that branches also exhibits self-similarity. Okay, I'm going to do a little investigation regarding the Koch snowflake. I gave you some triangular grid paper, and I'm going to get you some crayons in just a second. You're going to create a seed triangle, and you are going to build the Koch snowflake. And at each step, you're going to record some information about the snowflake that you've built. You're going to write down how many sides it has, what the length of each side is, and what the perimeter is. Okay? And then we're going to try to come up with some kind of formula for each of these things. So here's the triangular grid paper. This we're just going to call 1 unit, right? So that's how you're going to calculate the lengths. Just each little grid line is 1 unit. All right, so let's go through and fill in the table here. All right, so I've drawn the seed, and we already filled in the information for the seed. And then I've drawn step 1. So I put on my 3 triangles, and I want to count the number of sides. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides. All right, oops. 12 sides. What's the length of each side in step 1? 3. And then your perimeter, you have 12 sides. Each one has length 3, so your perimeter is 12 times 3, or 36. All right, so then if I do another step, on the middle third of each side of my snowflake, I'm going to put another little triangle. So that's 1, 2, 3, Well, I'll count the sides after. Yep, put them on every side, not just the new sides. Okay, so if I count the sides here, let's see. I'll do it in a different color so we don't lose track. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 7, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. 48 sides in step 2. What's the length of each side? 1. Each is one little triangle. So I have length 1, which means my perimeter is 48 times 1, or 48. All right, so now I could try to draw step 3, but I'm out of grid lines, right? I'd have to do just a piece of a grid line, and I'd have these little itty bitty triangles, and I'd have a lot of them, and it's going to start to get hard to see what I'm doing. I might lose count. So instead of trying to draw step 3, I'm going to see if we can come up with a conjecture about the patterns here. So what's happening to the number of sides? Times 4. Yeah, you might recognize this list as times 4, times 4. 48 times 4 would be 192. And then how about this list? Any patterns here? Divided by 3 or times a third. It's the same thing, right? What's 1 times a third? 1/3. Or 1 divided by 3, a third. And then we can multiply 192 times a third, and what do you get? Or 192 divided by 3? 64. Good. And then we can just keep following this pattern. What's 192 times 4? 768. A third times a third is a ninth. 768 divided by 9? 85 and a third. Good. Okay, so now I want to try to write a formula for M, for L, and for P. I can use recursive or explicit. We've been working with sequences and writing formulas for a while now. How could I write, say, an explicit formula for M? Yeah, Ryan? You start with a 3, and we're multiplying by 4 over and over again, n times, so we raise to the n. Good. Right, so our seed was a 3, so we start with a 3, and then we go times 4, times 4, times 4, and repeatedly multiplying by 4 is the same as doing 4 to the n. That's how we denote repeated multiplication, is with an exponent. And then how about for L? Or actually, let's do a recursive formula for M first. How would I write how to get from one term to the next in this list? The previous number in the list times 4. Good. All right, let's look at L, the length of each side. Recursive or explicit, whichever one you want. Give me a formula. Three. You're close. So you're saying 9 times 1/3. Where do I put the n? In the exponent. Yeah. The way you were saying it, it sounded like multiplication. I think you knew what you were saying, but it just was a little bit off. So I start with a 9, right? That's my seed. And then I'm multiplying by a third over and over and over again. And repeated multiplication, you denote with an exponent. So this is 9 times a third times a third times a third, n times. All right, so my recursive rule, what would that be? Divided by 3 or times a third, whichever way you like to write it. All right, and then for perimeter, how are we generally figuring out perimeter? M times L, yeah. The number of sides times the length of each side. So if I use my formulas, I can actually multiply these together. What's 3 times 9? 27, right? Because this is all multiplication, so I can do the multiplication in any order. So I'm looking at the 3 and the 9 first. What's 4 times a third? 1 or 4/3, yeah, to the n. So it looks like 4/3 is the number that you repeatedly multiply by. Is that true? Is 27 times 4/3 equal to 36? So let me check on a calculator. I'll do it on mine just to show you all. So 27 times 4/3 is 36, times 4/3 is 48, times 4/3 is 64. So that looks like a good pattern, which means that my recursive formula is going to be p sub n minus 1 times 4/3. All right, is 4/3 bigger than 1 or smaller than 1? Bigger than 1. So if you multiply something by a number bigger than 1, does it get bigger or smaller? Bigger. Multiply by a number bigger than 1, and the answer is going to be bigger than the number you started with. So that means that at every step here, my perimeter gets bigger, right? 27, 36, 48, 64, 85 and a third, they're just getting bigger and bigger and bigger and bigger. So that is good evidence to support our original guess that the perimeter is infinite, goes to infinity. Okay, so let's see, we did this in the table. We did this in the table. We did this in the table. Okay, calculate the perimeter of the 10th step of the Koch snowflake if we started with a side of length 9. So I know my perimeter. We had a formula, 27 times 4/3 to the n. Right, so if I want the perimeter of step 10, I would do p sub 10, 27 times 4/3 to the 10th. 27 times 4/3. Oops, that should be a times. To the 10th. All right, I have 479.46. So there's my perimeter at step 10. So what can you say about the perimeter of the actual Koch snowflake, the one that you would get if you could do this for infinity? What would its perimeter be? Really long, right? It just keeps getting longer and longer and longer at every step, so its perimeter would have to be infinite. Are you surprised? No. We guessed this at the very beginning, right? No. We thought this was the case. We already thought that this was true, that this infinite object would have an infinite perimeter. All right, let's look at the area of the Koch snowflake. In order to study the area, it will be helpful to be able to calculate the area of an equilateral triangle. So you have a triangle where all 3 sides are the same. What's your standard area of a triangle? Anybody know it off the top of your head? 1/2 base times height, but the height would be this guy, right? That's your height, and your base would be S. So we're going to use an alternative version of the area of an equilateral triangle. Instead of using 1/2 base times height, we want a formula that has just S in it. So I believe, if I remember it correctly, that it is S squared times the square root of 3 over 4. All right, so the area of an equilateral triangle is S squared times the square root of 3 over 4. So let's say I have, just for a little practice, I have an equilateral triangle. All 3 sides have length 10, right? The area of this triangle would be 10 squared times the square root of 3 divided by 4. So that would be 100 times the square root of 3 divided by 4. And then you can just have your calculator do the work here. 100 times the square root of 3 divided by 4. About 43. Not so bad, right? You may not have seen this formula before, but it's just an alternative way of calculating the area of a triangle if that triangle happens to be equilateral. You okay with it? Take my word for it that this is true? Okay. Okay, so whatever time is available, we're going to begin filling in this table. We have plenty of time, so I'm gonna make you do some of this. I want you to write down at least 5 decimal places for each entry, except for the last column that you can round to 1 decimal place. So I've got the first 2 steps done. So this table is helping you calculate the area of the snowflake at each step, right? So for the seed, each side is length 9, right? It's a single triangle. The proximate area of each triangle, this one you get, this is where we use that formula S squared radical 3 over 4. So in this case, I did 9 squared times the square root of 3 over 4. You get 35.07. And then we had no area before the seed, so this is how much you add, and this is my area at the first step, 35.1. So all I've done here is take the area of the seed. All right, then, I don't have a new grid here. All right, so the area of this seed, I'm just going to outline it. Area of the seed is 35.1, right? And then I'm adding on 3 new triangles. These 3 guys are getting added on. So I have all the area that I had at the seed stays, and then I add some more area. These 3 green triangles get added on. All right, so let's go back to my table and fill in what they're asking me for. So the side length of each attached triangle, at step 1, I'm attaching 3 triangles. They have side length of 3. I'm attaching 3 of them. The approximate area of each attached triangle, well, you take the side length, and you do the side length squared times the square root of 3 divided by 4, and you get 3.89711. And then you say that each triangle that I added on has that area, and I added 3 of them. So you do 3 times the area of each one, and that's the total area that you added on to the seed. Does that make sense? Okay. And then you take this area that you added to the seed, you add that to the area you had at the previous step, and that gives you the 46.8 at the end of step 1. All right, so see if you can just do step 2. Okay, so let's discuss here. I'm going to go back to the picture. Here's a picture of step 2. At step 2, I added some triangles on, right? So many of you did your pictures color-coded, and it really helped to figure out how many triangles you added on at any given step. So I'm shading all of my added triangles in this purpley color here. All right, so how many of those purple triangles are there in the picture? 12. Yeah, so I added 12 triangles. When I went from step 1 to step 2, I attached 12 little triangles. What's the side length of each of those little triangles? 1. So that's where my 12 and my 1 come from. Okay, each one has side length 1. There are 12 of them. So what I would like to know is what is the area of each one, right? So what is the area of each of those purple triangles? Well, I use my area formula, s squared times the square root of 3 over 4. So I'm going to have 1 squared times the square root of 3 divided by 4. And a big sticking point for many people was just knowing how to put this into your individual calculator. So if you need help with that, just let me know and I'll show you. And we get 0.433012. All right, so I have each of my purple triangles has area 0.433, and I have 12 of them, right? So I'm going to figure out how much area I added to my previous step. I say, well, I added 12 triangles that each have this area, so I'm going to multiply by 12, and I get 5.19615. So that's the total area I added on. When I went from step 1 to step 2, this is the area that got added to the snowflake. So I'm going to add my 46.8 plus this, and I get 51.99 or 52. Something close to that. You might have rounded a little bit, as long as you have the general gist. All right, this is a huge pain, all these calculations. And you're doing the same calculations over and over again, right? What computer program would really help us do this? Excel. Yeah, so I did this in Excel. Lucky for you guys. Okay, so here's my Excel sheet. You can see that all the numbers we already had were in it. The number that we just calculated was step 2, side length 1, number of triangles 12. It's got the 0.433, 5.19, and it's got 51.96 as the total area. So I just had Excel. I programmed the Excel spreadsheet to do all the calculations that we were just doing by hand. Take a look at the total area column. What do you notice? What's happening to the total area as we increase the number of iterations? At first it's growing, right? 35 to 46, that's a big jump. That's a jump of 11 units, square units, right? 46 to 51, that's a jump of 5 units. Then about 52 to 54, a jump of 2 units, a jump of 1 unit, a jump of like a half, jump of 2/10, a jump of 1/10, right? So my jumps, my area from at each step, it's growing, but it's growing by smaller and smaller amounts. And by the time we get down to the bottom here, from between step 21 and 22, it grew by 1/10, 100,000th, 10,000, 1/1,000,000th, right? Barely anything at all. So what do you think about the area? Is the area finite? Yeah, it's growing, but it has a limiting value, right? It can't ever get bigger. It can't go towards infinity, right? Right, so let's look at that again. Hold on. So on the far left column here, I made an additional column where I added the ratio, which was the area at step n to the area of the seed, to the original area. So I'm taking the area from this column, the total area column, and I'm dividing by the original area, which was 35.07, area of the seed. So I'm taking this ratio, and what do you notice as we get further down the list? It levels off at 1.6. The ratio of the Koch Snowflake to the seed area is 1.6. It almost, yeah. Yeah, it's actually not the golden ratio. You might expect it to be. The golden ratio is 1.61803. Approximately. This is exactly 1.6. Exactly 1.6. All right, so here are some conclusions about the Koch Snowflake. So these are all formulas that we wrote together. I just wanted to have them all in one place for you to reference. So the number of sides at step n is 4 times the previous number of sides, or 3 times 4 to the n. The length of each side at step n is 1/3 of the previous length, or the given side length of the seed triangle times 1/3 to the n, whatever the given original side length is. And then we've got formulas for perimeter that we developed. After infinitely many iterations, the perimeter of the Koch Snowflake is infinite. And after infinitely many iterations, the area of the Koch Snowflake is 1.6 times the area of the seed. So if you know the area of the seed, you know the area of the final infinite Koch Snowflake. And that area turns out to be finite. Are you surprised? Yeah. So it has finite area. And if you go back and think about how we're going to draw it, let's look at this picture. Will my Koch Snowflake ever leave that grid? It won't ever grow bigger than a single piece of paper, so its area has to be finite. You can keep drawing and drawing forever without needing more paper. So its area is stuck on a piece of paper. Yeah, with a very sharp pencil. Good. All right, so those are all our conclusions about the Koch Snowflake. These formulas are also all on the front page of your packet, then you can use them on the test 3.